Good morning, everyone. Let's talk about cameras today. So we will understand how general cameras are made, the effects when you change different parameters of the cameras. But the main intention is to understand how a camera can be mathematically represented. So that given a 3D scene, we can use those mathematical representations to obtain a representation of the image. And then we can understand how images are created using the cameras. So after we study cameras, we will study how to compute the parameters of the cameras that are inside the cameras, and also the parameters that are outside the camera. That means the look pose of the camera, the location and the orientation of the camera, how to obtain those. This is called camera calibration. After that, we will see how when two cameras are there, how the images are made and how the images relate to each other in those two cameras. And then finally, we'll understand how to make a 3D reconstruction. This area is an extremely important area these days because people are very much interested in 3D reconstruction. Okay. So we'll in this lesson we'll talk about cameras with lenses, what depth of field means, field of view, and then some problems with the lens aberrations, and briefly about digital sensors. So you can see a picture of very old cameras, and you can see there is a lens in the camera, and then at the back of the camera there is a film which can record the light that impinges on that camera. So this experiment was done by this person called Paul Debevec. What he did was he removed the lens of the camera here and put a cardboard with a hole in that, small prick in that. So this was the image that he was able to make using that. So you can see light strikes the sensor of the camera, light strike the sensor. But one thing is there is no focus. There's no focus. And also at the corners, not much light has come into the corners. So we will understand by looking at this how a lens is useful in a camera. Okay. So now all these experiments we have done in the past are useful for us to understand this. For example, we had the so-called pinhole camera, this one, where we had a toothpaste tube and we made a little hole in the toothpaste tube, and we had one more toothpaste tube sliding back and forth inside that. And we had a tissue paper or something here, and we look from here, and then we would be able to see an upside down image of the scene that you see. An upside down image like so, right? This is called the pinhole camera model. The thing about pinhole camera model is light rays do not bend. They go as straight lines, right? Light rays do not bend. So this is the thing about the pinhole camera model. So we have to understand the pinhole camera model and then understand when a lens is added, what happens. Yeah. So as usual, if you have any question, please don't hesitate to type the question, or you can turn on the camera and turn on the mic and ask at any time. So now you can see in this image, the image is blurred. Why is the image blurred? We can understand that the reason is this. Now think about this. Okay, this is the tree or something in the 3D scene. And then we have the hole. So I'll draw that in a one-dimensional manner. Assume that this is the hole. And this is the film. This is the film or the CCD or the CMOS sensor. My question is, if you take one point in this film, to what points in the scene does this correspond to? Of course, you can understand that the light comes from that point to this without a problem. Yes. And the very extreme is light can come from here. I'm sorry, I cannot draw straight lines using this. light can come from this extreme also. You can see. Just touching that edge, you can. So you can see one point in this CMOS sensor or the camera sensor, usually they are CMOS sensors, right? One point there corresponds to many points in the same. So as a result, there is blur, right? When you take the second point, some of those points in the first scene part will correspond, and like that. So all these um, uh, points will receive light from multiple points in the scene. As a result, there is blur. Now, to reduce blur, you will tell me that we can make this prick or the hole small and smaller. So we make it very small so that only this ray and very close by rays can go in. But what happens then? Then the amount of light that comes and strikes the CMOS reduces. Therefore, you have to increase the sensitivity of the sensor, CMOS sensor. That is done by increasing the ISO of the camera. Those who have used cameras know that these parameters. Okay, so let's study this further. Now, if the prick is large, maybe 2 millimeters, there is blur. You can understand that. So you make it smaller, the blur reduces. Make it even smaller, the blur reduces. Maybe let's say 0.35 millimeters, the blur is gone, but you don't have enough light, but that's okay. Somehow you amplify that. But now our intention is to even make it even smaller. But when you make it even smaller, the so-called diffraction effects take place. What that means is when light goes through a slit like this, at the edge, light bends, right? Maybe you know that. This is called not refraction, this is called diffraction. It's called diffraction effects. Diffraction happens. Because of that, blur comes again. So therefore, this pinhole model is not going to be helpful in making sharp and bright images, but we have to study that. So to correct these problems, you add a lens. Now you can see the beauty when you add a lens, all the light rays that are emanating from that one point in the scene, which is this, go and strike this one point in the film. So there is one-to-one correspondence between the object and the film. So therefore, you can get a sharp image. So this is called thin lens model. Rays passing through the center are not deviated. Thin hole projection model still holds. And we know that we have studied that in O levels, that this light ray that goes through the center of the lens does not bend. Light rays that go parallel to the optical axis, they go and strike the focus. I think we know these things. So this is that. All parallel rays converge to one point on the plane located at the focal length. So this is the focal length F. That's a focal point. Yeah. So, but other specific, so now this focusing happens at a specific distance. That is, now there, if you take a plane in the scene like this plane will be focused here. But if you take any other plane, like so, the light will not focus onto the film. Maybe it will focus somewhere here. So therefore, near the film, at the film, there is some larger image of that one point, larger than a point. So this is called the circle of confusion. Yeah, circle of confusion. Yeah. Okay, let's look at the thin lens formula, which we have studied in O levels. What is the relation between the focal length, the distance of the object from the optical center, and the distance at which the object will be in focus? So we can look at the similar triangles for this. So if you take these two triangles, you can see this is y prime, and this is, let's call this y, and this distance is d, this distance is d prime. So you know that y prime divided by y is d prime divided by d because these are similar triangles. Similar triangle means the angles are the same. Then we can consider this triangle. In this triangle, you can see f and d prime minus f. So this distance divided by y, this distance, and d prime minus f, and then we have one more. So by combining these two equations, you can obtain the thinless formula, which you have done in O-levels. Okay. Okay, now let's look at the concept of depth of field. You can see in this image, these regions are blurred. This region is blurred. Only a certain region is in focus. Similarly, in this image. So the region that is generally in focus is called the depth of field. This is a parameter of the lens of the camera. So controlling the depth of field is how do you do that? So then the lenses in the camera, actually not the glass lens, but the lens barrel, that has an opening, right? That's called the iris. So this opening can be large, like here, or this opening can be small, like here. Okay. Now consider this opening is large case. Now large part from the light coming, and a large portion of the lens is open, so light can go through from far away places than from the axis. So if you take this one light rays go here, another light ray, another light ray, and they go and focus here, right here. So not on the film. So this is the film or the CMOS sensor. I'll just write F there. So you can see the circle of confusion. So there is a circle of confusion here. Let's take item number 3. If you take item number 3, you can see still that problem is there. Item number 3 is too close to the lens. So light rays go like this, and they will focus somewhere here. And so therefore, here, there is the circle of confusion. But if you take this plane, plane number 2, that will be in focus. This plane will be in focus. So light rays going like that. The blue ones, they will go and focus here, and there will be just one single dot there. So you can see when your aperture is open, then only certain planes get focused. Other planes do not get focused. So you can see the depth of field is this concept. But when you close the aperture, almost all the points get focused, because now the light can go through only this one. But of course, you can understand when this happens, the amount of light that comes into the inside the camera is small. As a result, to make these kind of pictures, you have to have very good lighting, or you have to do this picture taking during daytime. Usually, pictures are taken during early in the morning. But the whole scene will be in focus. For landscape photography and so on, you use this one. This one. If you want to do a portrait photography, that means a picture of a girl posing for the picture, you use a large aperture like that. So this is called F number in the camera. So you can see this small depth of field versus large depth of field. So you can see all these are in focus. Here only a certain part is in focus. These are not focused. And then what is field of view? Field of view is like how much of the scene gets into the image. What determines field of view? So we can draw a plane of the camera. So this is, you can see that this is the CMOS sensor. You can see this angle corresponds to what can be seen from the image. So this angle you can get by dividing d by 2 by f and getting the tan inverse. That's the field of view. So larger focal length, smaller field of view. So you can see if you have a very uh, small focal length, the whole scene is in view, right? But if you increase the focal length, now slowly only parts of the scene are getting seen. So only this couple, and then you further increase the focal length, 50 millimeters, then a small part is seen. And even 85, even a smaller part, then under 35 and 300 and so on. So you can finally see only this part of the ship with a very large focal length. But these large focal length lenses are very expensive. One thing that people do is they do this when they move away from the scene and increase the focal length while moving away from the scene. So then the object more or less stays as at the same size in the image. But one thing that happens is the 3D nature of the scene is gone when that happens. 3D nature of the scene is gone. So you can see these are large field of view, small left, camera is close to the car, so the 3D nature of the car is seen. Small field of view, large F camera far from the car. So the 3D ness of the camera car is gone now, less. So when you make a picture of a person also, you would use an optimum focal length. Now here the focal length is small, so camera is too close to the girl and the face is too 3D. She will not be happy about this. Here the focal length is large. Camera is too far away from the girl and the face is flat. She will not like it. But this one is like optimum focal length and she'll be happy if you make a picture like that. So sometimes when you make portrait photography like that, you don't use a lens that can change the focal length. You have lenses with fixed focal length. We call them buttas. So those are very, very good and very sharp pictures can be made with those. Yeah. Okay. Yeah. So orthographic camera means there is no foveation over. That means is rays seem to come parallelly to the camera. So therefore things like that, the line parallelism in the picture also lines are parallel. But in this case, you can see this is called perspective imaging. The lines are no longer parallel in the image, right? Although they are parallel in the scene, in the image they are not parallel. So 3D nature is very visible. Weak perspective, increasing the focal length, you lose that. So the other effects are also there. You can click this and find out these effects. They are interesting. Yeah. And then there are problems with the lenses. So these lenses, I have heard that they make lenses by slowly cooling the glass, molten silica. So they are very expensive. Lenses are expensive. So one thing is, one problem is called vignetting. This cannot be observed very well in the modern lenses. At the edge, the light can escape. Like they do not no longer bend and go into the go and strike the film or the CMOS sensor. So therefore, at the very corners, you will see some darkness. This is called vignetting. And to make a picture look like an old picture, you can add a little bit of vignetting. Then people will think that it's an old picture. Because in the old photographs, they have seen these things. Yeah. Then one thing is a radial distortion. Now, if you take a rectangular grid like that, when there's no distortion, the lines are straight. But there's a thing called pincushion distortion. Then lines are bent like that. And then barrel distortion, lines are bent like that. And they are like a barrel here. So you can see this is an example of barrel distortion. So then there's a thing called spherical aberration. Spherical lenses do not focus light perfectly. Rays further away from the optical axis focus closer. Because of that reason, see, rays far away focus closer. So then there's another problem called chromatic aberration. A lens has different refractive indices for different wavelengths. So, for example, red does not bend as much as blue does. So at the outer edges, you can see a color halo because of that. So then let's look at the digital sensors. So earlier, the digital sensors used to be CCD sensors. Now they are mostly CMOS sensors. Digital camera replaces film with a sensor array. So charge coupled device CCD, complementary metal oxide semiconductor CMOS. So when you think about the image sensor, they do not have three sensors for the three colors. They have only one sensor, but filters on top. So you can see the blue filter is there, the green filter is there, and the red filter is there. So certain pixels only receive blue light. Certain pixels only receive green light, and so on. So, so you can see some pixels they don't have blue, for example. So you have to interpolate from the adjacent pixels. So this process is called demosaicing, estimation of missing components from neighboring pixels. Why more green? Because human eye is more sensitive to green. That's the reason for having twice as many green pixels than red or blue pixels in a camera. So yeah, okay. So this is called Halamoa. So you this happens when you have a pattern and your sensors interpolation algorithm plays with that. So that's why sometimes when you go for a TV show or something, you are asked not to wear thin striped shirts. So read about these things. They are not very much a part of this course because this is not a camera course and I don't know about cameras too much also. So miscellaneous camera artifacts. So noise is there, low light. When there's low light, you notice noise. So then you usually increase the ISO. Uh, then there are stuck pixels that cannot be changed. So these are manufacturing fault. Then in camera processing, over sharpening can produce halos like that. And then JPG artifacts are there. I think this is JPG artifact, not in camera processing artifact. Then blooming, CCD charge overflowing in neighboring pixels, and then color artifacts, color more purple fringing from micro lenses and so on are there. So these artifacts, you should be aware of those. Yes. Okay. So some history about cameras. So people knew about these cameras in BC, 470 BC, and then Kodak made the first fully digital camera in 1990 and so on. This is supposed to be the first digitally scanned photograph. So number of cameras, digital cameras, have become extremely large due to the advent of the mobile phones. These are compact digital cameras, DSLR cameras, and then because of that, the number of cameras are billions now because everyone seems to have a camera. That's about the cameras. So if you have any question about cameras, please ask.
So is the smartphones are different from the digital cameras?
Are smartphone cameras different from digital cameras? Is the question, right? So if you take the smartphone camera, it does not have the ability to change the focal length, right? It doesn't have the ability. So several cameras are there in the smartphone, maybe three cameras. So they have three different focal lengths. So they simulate this by, I think, digitally. But if you take a DSLR camera, you can change the focal length of the lens. And the CMOS sensor is quite large in those. So therefore, the adjacent pixels will have different colors. If you take a phone camera, the close by pixels will sort of have the same color because the sensor size is very small and the lenses are not so good. So if you want to do professional photography, wedding photography, and so on, then you need a, so-called expensive camera. Yeah, thank you for that question. Uh, when we start studying about this focal length and so on, we can look at some real cameras and do some calculations about the image size and so on. Okay, now let's look at the geometry of a single camera, and then we'll be able to understand all the parameters of the cameras like focal length, uh, not all the parameters, uh, focal length, then the principal point coordinates, camera location, camera pose, how to estimate that and how they affect in image making. That's what we are going to look at now. So we will see the motivation, look at the perspective projection model, intrinsic camera parameters that are inside the camera, extrinsic camera parameters that are outside the camera, how to calibrate cameras, and the meaning of triangulation. Okay. So given an image, can we recover the 3D structure? With one image, you cannot. That's why human beings are given two eyes. But with certain assumptions in the scene, that means uh, parallel lines and perpendicular lines being there in the image, you can, up to a certain extent, recover the 3D structure. Uh, how did people make these kind of images? So how they did was they had the uh, aperture very small, so that the whole scene is in focus and kept the camera near the pumpkin. That's how they were able to make this. So here also a similar one because the far away parts of the scene, the Tower of Pisa, as well as the person is in focus. Okay. So now let's look at the so-called single view ambiguity. The question is this. Now you can see the CCD in the camera or the CMOS of the film. Okay. CMOS of the camera. Actually, if this is the lens of the camera and this is the optical axis of the camera and this is the 3D object in the camera and this is the scene. Give me a minute. Yeah, sorry about that. So uh, light goes through the lens and makes this image. Now this is the image. Okay, this is the 3D scene. This is the lens. So you can see this is the film. So the film or the sensor is behind the camera, okay, behind the lens. But because of these similar triangles, it is okay to draw it in front of the lens also. They represent the same thing. So that's uh, what is represented here in front of the uh, camera or in front of the lens. We have the CMOS or the film. But the question is not that. Question is now in the film, image X is given. This is an image. Small x is an image. So this is a light ray that goes through this small x and connecting with the camera center. This is the camera center. Where can the 3D location be? There's a 3D location that gave rise to this image small x. Where is the 3D location? So you can see that 3D location obviously must be on this somewhere on this ray, right? Where? Is it here? Is it there? Or is it there? You can see that any of these locations are possible locations. So you can see camera's action is converting anything along the ray to a single point, right? So from 3D to 2D conversion is what cameras do. Okay, so that's why we can make 3D structures like that, giving rise to beautiful images like this. This is the ambiguity. So people can draw pictures like that also. And then this is called anamorphic perspective. So these artists, they carefully drew these things. If you uh, change the viewpoint to this somehow, then you can see this is the image that has been there. So it reminds people of the passing nature of worldly things, right? Okay, so our goal is to recover the 3D structure. With certain assumptions hold, we can recover the structure from a single view. In general, we need multiple views to get the 3D structure. But first, we need to understand the geometry of a single camera. So let's understand the perspective projection model, intrinsic camera parameters and extrinsic camera parameters. Okay, this is the perspective projection model. So I will explain again what this means. Um, so you can see the camera center. Camera center is a center of the lens. So this is the lens. This is the optical axis. Axis going through the lens, perpendicular to the lens. So there is a three-dimensional object, maybe an arrow that we call capital X. And light rays go through the lens without bending from the center, right? Going through the optical center, do not bend. And an image is created here. And that is our image plane, right? This is the image plane. That's our image plane. This image plane is this one. You can, as I told before, the image plane can be drawn in front of the center because of the similar triangles. This capital X, the 3D point is this one. And where the image is made, this is actually this one. Optical axis, obviously, we drew that this is the optical axis, right? This is the optical axis. That optical axis is this one. We call it principal axis or optical axis. And then finally, the camera center is exactly this center. That's the camera center. Okay, so I hope you understand the actual geometry and the geometry represented in the figure. Okay, so now let me draw a two-dimensional version of that. Normalized camera coordinate system, camera center is at the origin, principal axis is z-axis, x and y-axis of the image plane are parallel to the x and y-axis of the world. That also you can see this is the y-axis of the image. This is the y-axis of the world. They are parallel. This is the x-axis of the image. This is the x-axis of the world. They are parallel. Z-axis, they coincide. Okay, so this is the geometry drawn in 2D. Okay, let's understand this. This is the capital X. So I represent capital X is in three coordinates, X, Y, and Z. And the image point, this small x is this one. That is represented using small x and small y because it has two coordinates. And you can see the focal length and you can see the distance to that object, capital Z. Now the question is, when you consider this triangle and this triangle, this triangle, how do you compute the value of this height? This height. That height is y, small y, this number. How do you compute that? I'll let you compute that. Think about it, please, briefly. So you can see from the similar triangles, it is very easy to compute that. This height is y, capital Y. This height is small y. This distance is capital Z. This distance is small x. So you can see very easily you can get this small y divided by capital Y, similar triangles, is equal to f divided by z. So you can get the formula small y is equal to Fy divided by Z. So very simple equation. A similar equation is there for X also. Those are the equations. I hope it is clear. But now we want to represent them using matrices. This is how you represent them using matrices. We have a special matrix called the camera matrix. That size of that matrix is 3 rows and 4 columns. It's a 3 by 4 matrix. The world point capital X, this one, it is this, that is represented using not only 3 coordinates but a 1 at the bottom. It's a 4 by 1 matrix or a 4 by 1 vector, 4 vector. And the result that you get, which includes these quantities, is a 3 by 1 vector. Okay, let's see how this works. So we have F, we have 0, and we have 0. And you know that this F multiplies which one? F multiplies with this X, right? Right? And then this 0 multiplies with this Y. And this 0 multiplies with this Z. And then finally this 0 multiplies with this 1. So all are 0. So Fx is what you get. Is that clear for you? Now compute the second row. In the second row, this 0 multiplies this Y, this X. F multiplies this Y. This 0 multiplies this Z. This 0 multiplies this 1. So finally what you get is Fy. And then in the last row, 0, 0, 1, 0. So therefore, this is the only one that is giving a non-zero value, that is Z. Then how do you get the Cartesian coordinates? So these are the Cartesian coordinates, small x and small y. The small x and small y are the Cartesian coordinates. To get them, you can see this quantity fx has to be divided by z. And if this quantity fy has to be divided by z. This is exactly what we can do. So, so these are called homogeneous coordinate vector of the image point. Homogeneous coordinate vector of the 3D point, we call it homogeneous because we have added this last number. It has more meaning than that. Later on, we can understand that. Okay, so you can see small x is fx divided by z, small y is fy divided by z. You divide by the last coordinate to obtain the Cartesian coordinates. So this is the projection equation. So P is the camera matrix. X is a 4 by 1 vector in 3D. Small x is a 3 by 1 vector on the image plane. Although it is a 3 by 1 vector, it's x and y we can recover by dividing the last number. So this lambda is an unknown scale. So equality up to a scale, you can write x equals 3 line equal px. It's a special way of representing that. Okay, so now what we want to do is we have to slowly start adding other parameters. So let's do that. So one thing is when you think about the camera calibration overview, there is the world coordinate system. This point x is defined with respect to the world coordinate system. There's a rotation and translation between the world coordinate system and the camera's coordinate system. So camera calibration means figuring out transformation from world coordinate system to the image coordinate system. So first of all, we have capital X, the 3D point in the world, and world to camera coordinate transformation. This is a rotation matrix. We will look at that in detail. Translation matrix, a 0 matrix and 1. And then the canonical projection matrix, I means the 3 by 3 identity matrix, 0. and K is the 3 by 3 pixel coordinate transformation matrix. So we will look at them in detail, and this is the 2D point. So we look at them in detail. Okay. We call this extrinsic camera parameters because they are outside the camera, because they have rotation and translation. Intrinsic camera parameters, those are internal to the camera. Principal point, scaling factors, and the focal length. So this whole thing we call P equals KRT. This is something that you have to remember, KRT. Okay. Now let's keep on adding other things that are required in this. First of all, the so-called principal point. Principal point means this. Now, in the imaging geometry that we had, the principal point was at the center. So this is the 0, 0. This is our 0, 0. But in images, we don't call the middle one 0, 0. No, we call a corner 0, 0. Actually, we call the top left 0, 0. So therefore, this P, or the so-called principal point, will have some x and y coordinates. We have to incorporate that. In the normalized coordinate system, the origin of the image is at the principal point. In the image coordinate system, the origin is the corner. So how do you incorporate that? We want the principal point to map to Px, Py instead of 0, 0. So therefore, we have to add Px and Py to this equation. This is very simple. But when you have this in the equation, how do we capture that in the matrix form? So if x, z times Px is required, why do we need z times Px? Because remember, we are dividing that by z. And then the numbers in the matrix are F0, Px0. Now you can see it's beautiful, right? So if you think about this, how I will give you a minute to think about this. Okay. As you know, this 0 multiplies this 1. This Px multiplies z. This 0 multiplies x. This f multiplies y, right? Sorry, x. So you can say fx plus zpx is what you get from here. This is fine, because when we divide that by z, we get the equation at the top. Similarly for the y coordinates, and last one is z. So you can see in the matrix now we have captured the focal length as well as the principal point coordinates. But one thing that you need to remember is those principal point coordinates are uh, they are all in meters or millimeters. They are all in meters or millimeters, not in pixels. Finally, what we want is to get them in pixels. Give me a minute. Students are called. Yeah. So I hope that this is clear to you, how we get this. If there's any question, please let me know. So when we divide this quantity by z, right, you get this, right? When you divide this quantity by z, you get this one. Okay, so let's move forward. Now we have the camera matrix up to this level. Uh, now you can see that we can even decompose that in this fashion. It is possible. You can verify by yourself f times 1, 0 times 0, px times 0, like that. You get this one if you do this matrix multiplication. This is called K, the camera calibration matrix. This is called I0. So this part is I. This part is I. Actually, we call it I3 sometimes, right? I3, identity matrix. And this is the zero vector. So we call it the zero vector. So this one, as you know, is 3 by 1. This one is a 3 by 3 matrix. So this P, as we saw before, PKI0 is what we have right now. So what are the units of the focal length and principal point? They are in meters or millimeters. What units do we want for measuring image coordinates? We want pixel units. Now this transformation we have to do, we need to introduce scaling factors for mapping from world to pixel units. This we do using looking at the camera sensor. If you think about the camera sensor, they will have this parameter mx, means how many pixels per meter in horizontal direction. My means how many pixels per meter in vertical direction. If you take the pixel size, it is 1 over mx times 1 over my. So this thing is in meters. So what we want to do is we apply these scaling factors mx and my. So when this myx multiplies f, my multiplies f, this mx multiplies px and py, and so on. So therefore, you will get alpha x and alpha y, beta x and beta y. These are in pixel coordinates. Focal length in x direction in pixel coordinates, focal length in y direction in pixels, principal point in pixels, principal point in pixels. So you can see now we have converted from meters or millimeters to pixel. One more thing that we have to do is to apply the rotation and translation with respect to the camera is somewhere, maybe the corner of the room, but with respect to the corner of the room, we have to get the camera coordinate system. Yeah, this R and T, find that. So in non-homogeneous coordinates, the transformation from world to normalized camera coordinate system is given by this. So please remember that, but when you think about it, you can understand. If you have done robotics, maybe you will know. So this is the camera center in non-homogeneous coordinates, C tilde. So maybe this x tilde is there. So you subtract c from that and then apply the rotation to get the x in with respect to the camera. Now it is with respect to the camera. Okay. Coordinates of the point in world frame. Coordinates of the camera center in the world frame. This is 3 by 3 rotation matrix. Coordinates of the point in normalized camera frame. So we can write this as Rx plus T. So Rx plus T is there. So now we can get capital X with respect to the camera now. So in homogeneous coordinates, we have to put a 1 there. Please remember that. And then you can see x camel 1. You get by multiplying this by R and T is there. 0 T. 0 is 3 by 1. 0. Okay. And the 1 is there. So in homogeneous coordinates, RT 0, 1, X cam. The transformation from normalized 3D coordinates to pixel image coordinates. That is this. Okay. Finally, when you incorporate that, you will see finally lambda x equals k rtx, t is equal to minus rc. So this is something that you have to remember. So imaging equation is x equals k rtx. So t is equal to minus rc, coordinates of the camera center in the world frame. What is the projection of the camera center in the world frame? So this I will not say. This is the camera center is null space of the projection matrix. That's okay. So summary P equals K RT is the camera matrix. Intrinsic parameters K mx my and beta x beta y, alpha x alpha y are the intrinsic parameters. Principal point coordinates, focal length, and the principal magnification factors mx and my. Skew, we did not consider in this, but when you do an actual camera calibration, that will also come into the picture. Radial distortion, important in practice, but we have not incorporated that into the equation. Then extrinsic parameters are there. Rotation and translation related to the world coordinate system. Yes, that's R and T. So let's do this small exercise. Let me get rid of this something. Okay, let's do this problem. Uh, In the imaging sensor Alpha 7RV full frame mirrorless interchangeable lens camera, let's look at this camera first of all. Right? This is an expensive camera. So it's a Sony camera. I don't know how to go to the original manufacturer's website. I want to go to the Sony website. Let's go to the this is the camera, right? 7RV. That's the camera I have looked at. It's a very expensive cameras. Sensor camera. So you can see the CCD here. Sorry, CMOS sensor here. If you look at the specifications, they will tell you the parameters of that, right? Uh, the resolution and so on you can find. Video resolution. You see the specifications. Image resolution is what I want to see. Image size. So you can see large image, right? It's a large, very large sensor. And there's a sensor has a size also. So we can find what this sensor is. It's very hard to locate. They don't tell you, but that sensor is by Sony. Sony. So we had to ask what is the sensor used for this camera and then look for that sensor. Yeah. So that's what I have written. So you can see I have used those numbers. In the imaging sensor, Alpha 7RV full frame, mirrorless interchangeable lens, camera parameters are 35mm full frame, 35.7 and 23.8. You can see I have written those numbers here. That's the width of the sensor, and this is the height of the sensor. And this has that many pixels. This has that many pixels, and diagonal length is also there. Uh, find the pixel size. How can you find the pixel size? Meters is there and number of pixels is there, right? So in millimeters, you can find the pixel size. So I think both will give the same. Uh, 35.7 millimeters divided by 9,500 ohm. That's the pixel size in millimeters. The same answer you will get by dividing 6,336, uh, 23.8 by 6,336. So if you get the inverse of that, these are the pixels per meter parameters. Yes. Now the question is, if you have an imaging geometry like that, maybe your focal length is 40 millimeters. 40 millimeters, okay? And then your distance from scene, camera to scene is, let's say, 8 meters, like 8,000 meters, 8,000 millimeters. And if this is a size of the object, 400 pixels, 4,000 pixels. What is the size in the scene? So 4,000 pixels, you have to convert to millimeters, right? And then apply this one. So 4,000 pixels, you have to convert to millimeters. So divide by 6,336 times 23.8 millimeters is that one. What is the imaging geometry? This is F. This thing. Uh, to find the actual object size, you can have to divide this by 40 millimeters and multiply that by 8,000. That's the size of this object in millimeters. You can do the calculation. 4,000 divided by 6,336 multiplied by 3.8 times 8,000 divided by 40. 3,005 millimeters. That means approximately 3 meters. That's why you find the actual object size. If you know the distance to the object and that you know the object plane is perpendicular to the optical axis. Otherwise, it does not work, right? So if the object plane is not perpendicular to the optical axis, that means if your object is sort of like, is the ray, okay? Your object can be like this also, no? Still you get the same image, right? Even if your object is slanted, you get the same image. So then you have to do additional calculations to find. Okay, I hope this is clear. Any questions about the small question that we did? Okay. Okay, then let's move forward. So let's look at the calibration, how the calibration is done. So before that, let's do some coding. Save it. Okay. So, first of all, what we are going to do is we are going to take a 3D point cloud and make an image of that using the things that we learned. So for this, we need this imaging, this point cloud thing. I will send it to you over Zoom chat. There's a file called airplane.ply. So I sent it to you over Zoom chat. So please use that file. So I'm going to open that and then uh, uh, make an image of that. So, okay, so some code is there, some code is cumbersome, but I think we can enjoy doing this. So import numpy as np and then import ply file from, sorry, from ply file, im, import ply data, comma ply element. So these to read the point cloud file. Then import mat.lib file.splt. That's okay, I think. PCD point cloud data is equal to PLY data dot read. So you know that my images are in some certain folder now. Let me try to pick that. Airplane dot PLY. So first of all, assert PCD is not PCD is not none. Otherwise, you can run into problems because the file was not opened. Uh, so now if some error comes like that, what do we do? You can search for it on the Google and then it will tell you what to install. Pip install by file. That's it you have to do. So I hope that your systems are properly running now. So pip install by file. Install that package. Successfully installed. Now it should work. Works. Uh, Now the point cloud file has been opened. Now we have to extract the points. Points. These are not part of computer vision, but uh, we have to do this. Okay. np concatenate. np concatenate. Then PCD vertex X reshape. We have to reshape that 1 and -1, one vector, vertex Y, vertex Z, and so on is okay. So this is what we need. So points have been consequent. So if you can print the point shape and we can subtract the mean points equals points minus 3, 1. Okay. So you can display the points in 3D. It's okay. So you can see that this is 3D point cloud to the airplane. But actually, if you open that using Windows, it will show you a nice picture with some rendering. We cannot wait until it. Okay. Okay. So can you see that they have rendered? That's why the airplane looks so nice. Here, so that's the point cloud. But what we want to do is to make an image of that. This is the imaging part of that. So first of all, for that, we will have to remember we have x, y, z coordinate. We have to concatenate ones to make them homogeneous coordinates. So I will say ones equals np ones, uh, point dot shape 1, and then points I will concatenate ones along axis 0. Now if I get the shape, these are homogeneous points. You can see 4 times 1335 points are here. There are four of them are there, 4 rows. They are here 3 rows. Now it's okay. So I'll call them points themselves. That's okay, okay, because I will be writing homogeneous points. All right. So now the first of all, I had to now create the camera matrices. P1, camera 1. So for that, I need a rotation matrix R. Rotation matrix. So this rotation matrix, first rotation matrix, let's keep it as the identity matrix np dot array 1, 0, 0. Okay, that's the identity matrix for rotation matrix. And the translation matrix K, translation K, not K, T. Let's take T as 0, 0, and minus 4000. So minus 4000. That means along the z axis, I'm taking about minus 4000, looking at the image from bottom. Then I need the K. K we will keep as the identity matrix. We will not use any parameters for now. You can experiment at home, of course. Okay, that's my K. What is the, how do we compute the camera? Do you remember? P1 first camera is equal to, what is the equation? K R T X, right? And R and T must be concatenated. K matrix multiplication, this symbol, we have to concatenate NP dot concatenate R and T. That's the camera matrix. So you can even print the camera matrix. Then how do you get the image of that? To get the image, you can call them x1 because due to the first camera, p1 times points. And of course, to get the Cartesian points, you have to divide by the last coordinate. So x1 is done. Now let's create another camera matrix. As here I'm going to change the rotation matrix, not like this. I'm going to get the rotation matrix from, I'm going to write sines and cosines to get the rotation matrix. Uh, Let me say rotation matrix in 3D. So you can see, if you take called rotation matrix 3D, if I want to rotate around Z axis, if I want to rotate around Z axis, we see cos theta minus sine theta, cos theta. The theta I did not define. Let's rotate by about 30 degrees. So you have to convert them to radians, as you know. Cos theta, sine theta. Oh, cos theta is wrong. Minus sine theta. Okay, now it knows. Cos theta minus sine theta, cos theta. This is rotation around Z axis. Then translation matrix, let's keep the same. And then camera calibration matrix the same. Then we can construct P2. We can print P2. Then we can construct the points. And then these are the points. Now we have to visualize the points in 2D. Two figures. I want to do one figure, not two figures. I want to do one figure. One figure size 10 by 10 or something. I don't know. It's going to be too large. That's okay. Then AX dot scatter X points camera 1, Y points camera 2, X label, Y label, legend, show. I don't see nothing. Oh, I put AXS. Complaining it? Oh, let me get this shape first of all. Three by four. That's correct. Points, not shape. I, oh no, I know what has happened. It's getting concatenated again. Okay, let me call this row points. Row points. Then here, call it row points. So it's kept on getting concatenated. That's what happened. Mm. So now you can see. mm, rotation has happened, but there is a problem. This is not what I expected. I wanted it to rotate at this like 0, 0, that at the center. It's not done. It has not done that. Camera 1 is okay. 0, 0. Oh, okay. This is the problem, right? 0 points. I forgot to write 0 points here. Mean centering has not happened. Okay, mean centering did not happen. That's the problem. Okay, now you can see the camera 1. This airplane is there. Now it has been rotated by 30 degrees as we wanted because it's too large. Okay, so 3D point cloud is here. So we are making an image using this camera. This camera P1, there's no rotation in the camera. Rotation matrix is 1, 1, the identity matrix. Just looking from below. And then in this one, we have added a rotation of 30 degrees. So if you make this rotation 60 degrees, it will rotate by 60 degrees. So you can see more rotation here, 60 degrees, clock, counterclockwise. Okay, I'll give you some time to do this code. It's a nice code to do. So first of all, get this. And I'll give you this part in the, I will type in the Zoom chat because it's a cumbersome and totally useless code. So you can use that. And then this part you can code by yourself. It is important to do that. Understand uh, this multiplication, matrix multiplication. It is actually this one, right? So what we did in the slides. I'll be back. Please do this exercise. Now let's look at this problem. To do measurements using an image, assuming that the optical axis is perpendicular to the imaging plane, two flat objects lie there, a pair of earrings is kept in this plane. If the focal length of the camera is 8 millimeters and the pixel size is 2.2 micrometers times 2.2 micrometers, and the distance from the lens to the imaging plane is 720 millimeters, what is the size of the earrings? That's what we are going to compute by, first of all, extracting the earring. So I open the earrings image. This is that image. And then I convert that to hue, saturation, and value, HSV. Uh, and I am showing the, uh, first of all, the hue value, the saturation value, and value channel. So you can see hue, saturation, and value. You can see using saturation, you can extract the rings. So that's why we use the saturation channel. That means 0, 0, 1, channel number 1 to threshold using binary thresholding using Otsus. Then this black and white image is a thresholded binary image that also I'm showing here. This is that part. So please code this and think about the method of extracting the number of pixels corresponding to two earrings. For that, I will tell you the function. We had do some so-called morphological operations, and then we use the connected components with stats function for that. Connected components with stats. I will type that function out here so that you know that's what we will be doing. Do you think that it is best option to add a data set or picture from our code? I mean, using drive and local. I don't understand the question. Do you think what is best option? Add the data set or picture from our code? I'm sorry, I didn't understand the question. Okay, so let's proceed with this. So if you have the question, please let me know. First of all, let's do some morphological cleaning of this because there may be some strangled pixels, standard pixels. So W equals 5, and we want to create a morphological structuring element. Mm, Once that one, and then we do a morphological operation. Open, so-called opening, morphological opening, open image. So some pixels will be affected. So we want to show that here, open image. Yeah. So I will write that. So you can see the open image. There will be slight differences between this and that. You may not even notice, but it's okay. Now we have to do the so-called connected components with stats. That's the important operation that we are doing. Uh, Number of labels. There are static curriculum steps. Yeah. Yeah, this is fine. It's not important for the time being. Print. We can print the number of connected components, number of labels, and we can color map. We can get a color map image with this. See, we apply color map. Uh, Labels, number of labels, color map jet. So this color mapped image, I will show you color mapped. Yeah, that's what we wanted to do. Now you can see the background and the two foreground images have been identified using different colors. That means they have been segmented. So mm, now what I can do is I can print the areas of those pixels. Uh, to print the areas, we have to do something. Z is equal to 720 millimeters, right? F is equal to 8 millimeters, so 8 millimeters. Then I can O I comma S in enumerate stats. So I equals 0 means the background. We don't have to worry about that. Uh, Otherwise, let me say if I is not equal to 0, actually it's just keeping the background. So we can get the area XYWH area, and area must be quite large. And these are the centroids. I can print the area. So you can see centroids are there. area is 59,082 pixels, 59,157 pixels. So you can see these must be those areas. And then because we know the area, I can compute the area in millimeters. So that we have to do very carefully. Area in millimeters must be uh, area. We have to multiply by the pixel size. Remember, it's an area, not a length. A square divided by z squared multiplied by f squared. Different from the previous example that we did. There we did just multiplied by one, multiplied once, right? In this one, we just multiplied once. The reason is it was just a linear length. Now, because it is area, we have to multiply by the square of the pixel size, multiply square of z and divide by f. So now I can run that code. So you can see the actual areas we can find 2,300 millimeter square. That means if you get the square root of this, it's like uh, 25. Uh, what's the square root of this? Square root of 2,316. I just want to see the approximate size of the earring. It's like 5 centimeters by 5 centimeters, not this much. If you take, it's quite large, right? This is to calculation is wrong. 5 centimeters is a large earring, right? These are large, but they are not as large. 5 centimeters is too much. That's a code. So display part you don't need. So I can remove. This is how it's done. Very small piece of code just to estimate the earring. But for sorry, there was a power cut. So you can see it's a small piece of code, but we were able to extract the earring size. It's a beautiful one, right? If you want more explanation, I can give that. Okay. I hope it is okay. If you have any question, you can of course ask. So this is what we did. Now let's look at the calibration part where we try to obtain these camera matrix parameters. I will quickly go through that. Do not expect you to know this too much. So one way that you can do, because there are 12 parameters, you can have a calibration object like that. And using this calibration object that has these dots, of these dots, the 3D coordinates are known. That means the 3D coordinates like these are known, and we know the corresponding image coordinates. These are image coordinates. So therefore, we can construct an equation. For example, you can see in this scene, they very painstakingly measured the 3D coordinates, right? The three numbers are there, and the corresponding 2D coordinates. And because you have those two, you can obtain the values of the camera matrix. Geometry we know here, and we can, to get rid of this lambda, we can get the cross product 0 here. So cross product has been expanded here. So mathematics, I will not go through all of them. Then you have this particular equation. Then we need to find this P1, P2, P3. In each of these P1s, there are four numbers. So one match gives two linearly independent constraints. So there are so many point matches. So final linear system is this. It's like AP equals 0. 1, 2, 3D correspond to gives two linearly independent equations. The projection matrix has 11 degrees of freedom. Therefore, 6-point correspondences are required to do this calculation. This is called homogeneous least square. Find P minimizing AP squared. This one. This matrix is like A. Is like P. Uh, Solution is the eigenvector of A transpose A corresponding to the smallest eigenvalue. This is a theory of finding solutions for this. So of course you can do that in using Python. Yeah. So from here I will not explain how to do this too much after that. So linear calibration is easy for formula and solve, but it doesn't directly tell us the camera parameters. In particular, nonlinear methods are preferred. So for example, write down the objective function like this, krxi, that's the projection equation. And then you have xis, actual xis, and you can minimize this error in a manner to find k, r, and t. Yeah. So we briefly look at triangulation and then stop this. Triangulation means now you have three pictures of the same scene. So these are the corresponding points. You can see it's the left eye of the character. And given a projection of 3D points on two or more images. So this is the 3D point. Its projection here, its projection here, in projection here in three images. With known camera matrices, find the coordinates of the point. Find the 3D coordinates of the point. That's called triangulation. So we draw two rays from the camera centers. They may not intersect in the space, but we force them to intersect. We want to intersect two visual rays corresponding to x and 2. Uh, but because of noise and numerical errors, they don't meet exactly. So we minimize this distance, and then this distance can be minimized by computing the so-called reprojection errors, these errors. And then finally, we will find the uh, uh, numbers or the coordinates in capital X. So these kind of other different methods are there. I will not go through them. So, and the structure for motion is recovering both the 3D coordinates and the camera parameters, which we will briefly look at next time. So that's all for today. So we studied cameras. Will question like this come for exam? Of course. So if you have any question, you can ask. Otherwise, we are done for today. Thank you very much for participating in the class. I will upload this video. If you don't have a question, you can log off. Thank you. Thank you. So the data set question, I don't understand. We can give data set mounting drive and upload from the computer. What is the best? I don't understand this question actually. You have to ask that from me. Can you turn on the mic and ask this question? I cannot understand what you're saying.
එකනිස මේ අර සම්පස්ස දුන්න අපිට සයිමන්ට් එකක් එතකොට ඒක අර ෆොටෝස් එක අර සමහර ළමයි කරලා තිබුණේ ඩ්‍රයිව් එකෙන් මවුන්ට් කරලා එතකොට මම නම් කරේ මගේ මේ ලැප් එකෙන් ඒකේ තියෙන එක ෆෝල්ඩර් එකකින් අරන් දෙන එකෙන් තමයි ඒ කෝඩ් එකට මම ඒක අප්ලෝඩ් කරේ. එතකොට ඒ දෙකෙන් සර් මොකක් ඉෆිෂියන්සි එකක් තියෙනවද ඩ්‍රයිව් එකෙන් කරන එකෙන් සහ අපේ මේ ලැප් එකෙන් ෆොටෝස් එකක් දාන එකෙන්? ඒ දෙක අතර වෙනසක්.
එහෙම ඉතින් ඒක efficiency නෙවෙයි බලන්න ඕන අපිට computational power තියෙන්නේ කොතනද කියලා. ඒතකොට laptop එකේ sufficient computational power තියෙනවා නම් laptop එකේ තමයි කරන්න ඕන. දැන් drive එකේ කරද්දී ඒගොල්ලෝ දෙන computational power එකකින් අපි කරන්නේ. ඒතකොට ඒවා මදි වෙන වෙලාවක් එනවා computational power එක. ඒතකොට අපි pay කරලා ගන්න ඕන.
ආ
ඉතින් අපි ඉගෙන ගන්නත් අවශ්‍ය නිසා laptop එකේ කරන එක තමයි හොඳ වැඩේ. හරි දැන් මට තේරෙනවා මොකක්ද දාන්න කියලා.
හරි thank you sir.
Okay. Okay, then we can conclude. Thank you, everyone.